So in today's lecture, we will see the characterization techniques. So till today's, we had seen different characterization techniques like X-ray diffraction technique, scanning electron microscopy. So in today's lecture, we will see what is transmission electron microscopy. Right. So the material, the nanomaterials are fabricated by using different process like top-down and bottom-up approach. In today's session, we'll see the characterization techniques. That means the materials which have been characterized, by using XRD, scanning electron microscopy. And today we'll see what is transmission electron microscopy. So the overview of this particular lecture is what is transmission electron microscopy and what is the history of TEM. So TEM is nothing but transmission electron microscopy. TEM is nothing but transmission electron microscopy, right? And theory of TEM, the theoretical knowledge that you can obtain from using the TEM. And what is the instrumentation? In what way the transmission electron microscopy is useful, and what are the advantages and disadvantages of this particular transmission electron microscope? And overall, we'll see what is the summary and what are the references, right? So if you come to the history of transmission electron microscopy, in 1931, Max Knoll and Ernest Ruska developed the first transmission electron microscopy. So this transmission electron microscopy was first introduced in the year 1931 and considered the first electron microscopy. So after this, scanning electron microscopy has come. So before scanning electron microscopy, the TEM was introduced. So that's what 1931 Max Knoll and Ernest Ruska developed the first transmission electron microscopy in terms of electron microscopies, right? So this group was first interested in further developing the resolution of cathode ray oscilloscope. So this team started trying to develop the cathode ray oscilloscopes, right? This group was first introduced in further developing the resolution of cathode ray oscilloscope. After the World War II, Ruska was finally able to produce the first TEM with first TEM. So after World War II, Ruska was finally able to produce the first TEM, first transmission electron microscopy with 1 lakh resolution power, right? This was what he was able to produce. He was able to produce with the transmission electron microscopy. The resolution power is around 1 lakh plus resolution power. So if you come to the introduction part, scanning electron microscopy, the resolution of the image is limited only up to 10 to 20 nanometers. So if the scanning electron microscopy, the resolution of the image is limited only up to 10 to 20 nanometers. So this will not be useful to view the internal features. This will not be useful to view the internal features of an atom or to study the morphology of the sample of size say around 0.2 nanometers. Thus, to investigate the sample size up to 0.2 nanometers, so we investigate the sample size up to 0.2 nanometers, then people will prefer the transmission electron microscopy, right? That means transmission of electron beam into the sample, right? So SEM is used to determine the surface morphology, whereas TEM is used to determine the internal structure. So internal structure, that's what it is used to view the internal features of an atom or morphology of a sample of size around 0.2 nanometer. Thus, to examine the sample of size 0.2 nanometer, the transmission electron microscopy can be used. In this microscope, the image is obtained by transmitting the electrons through the specimen. In this microscope, the image is obtained by transmitting the electrons through the specimen. So if you see here, this is what the transmission electron microscopy is. Right, where the sample will be kept somewhere here, and the transmitted rays are penetrated into the sample, and this is what the block diagram is. This is what the block diagram of this particular transmission electron microscopy, where we have the electron source, condenser lens, right, condenser aperture, sample, objective lens, objective aperture, selected area aperture, intermediate lenses, and projective lens, and fluorescent screens, right? So these are some of the internal components of transmission electron microscopy. Right? So if you see what is the principle of working of transmission electron microscopy? So principle of working of transmission electron. Electron possess a wave-like character according to the dual nature of matter and radiation, which was proposed by de Broglie waves. So that is what the quantum mechanical principle. So the quantum mechanical principles we need to follow. We need to upload. We need to think about some of the quantum mechanical principles proposed by de Broglie, that wave particle duality, that electron possess a wave-like character. That is a dual nature, right? Electron sometimes behaves as a particle, sometimes behaves as a wave. So electron possess a wave-like character. So electron fitted into a vacuum from a heated filament. So with increasing the potential, we have small wavelength. It is analogous to, it is somewhat somehow the principal image, what we can, the principal form where we can understand the principle of working is similar to like Davison and Germer experiment, right? So in Davison Germer experiment, we use some high filament and we use some low filament. So low filament is used to, we use some low tension, not filaments. We need to tell low tension batteries and we use high tension batteries. So low tension batteries are used to heat the filament to dull red, and high tension batteries are used to accelerate the electron beam. So similarly, electron accelerates. So with that acceleration potential, we'll calculate the de Broglie wavelength as lambda equals to, lambda equals to h by under root 2 m capital E, right? Where capital M E equals to small e into V, where V is a charge and V is accelerating potential for the electron. So it is approximated to around 12.2 under root of V. So where we can observe some bump in the Davison Germer experiments around 54 volts, where we have some, the wavelength approximated is 1.6 angstroms, right? So this is what we study in case of Davison Germer experiment. So similarly, so that's why we tell electron possess wave-like character. Electrons emitted into vacuum form a heated filament with increased accelerating potential will have small wavelength. So such high energy electrons can penetrate a distance of several microns into the solid material. So when electrons heat electrons emitted into vacuum from a heated filament with increased accelerating potential, so those electrons will have the small wavelength, right? So the electrons will have the small wavelength. So such high energy electrons can penetrate distances of several microns into a solid. If these transmitted electrons could be focused, images with much better resolution. Focusing lies on the fact that electrons also behave as negatively charged particles and are therefore deflected by electric or magnetic fields. Right? Focusing lies on the fact that electrons also behave as negatively charged particles and are therefore deflected by electric or magnetic fields. So these are the different parts of one. We have the electron cannon. So this is what the first one. The first number represents the electron cannon. The first one represents the electron cannon, and we have the vacuum pumps. We have water supply to seal the instrument, vacuum chamber for observation, right? And we have certain screen for menu and image displays, and we have certain operation panel. So this is what some of the instruments. This is what the instrument generally we use to calculate the sample penetrate. We calculate the morphology. So morphology of the atom inside the sample, right? So this is what something over related to some this transmission micro. This is some power cable. We have fluorescent, right? We have electron gun. We have electron gun. We have the air suspensions. We have some specimen where the sample is to kept. That means the rays enter into the specimen like this. It will penetrate into the sample, and this penetrated sample can be viewed. Penetrated sample can be viewed by using the interface that we need to provide. So the electron source consists of the cathode as a cathode and anode. Cathode is nothing but electron emitter and anode is nothing but electron cathode. So here the cathode used is a tungsten element, a sunken filament, right? Sunken filament which emits electrons when being heated. So cathode is a tungsten filament which emits electron when being heated. A negative cap confines the electron into a loosely focused beam. Right. So the beam is then accelerated towards the specimen by the positive anode. Right. So the electron source, where we have the electron source consists of cathode and anode. Cathode is nothing but the electron emitter. Here we are taking the electron emitter as the tungsten filament, which emits electrons which when being heated. So a negative cap confines the electrons into a loosely focused beam. So the beam is then accelerated towards the specimen by the positive anode. So electron beam is tightly focused using electromagnetic lens and metal apertures. A platform equipped with a mechanical aim for holding the specimen and controlling its position. Controlling its position, right? When we have the electromagnetic lens system, that is what the imaging system. If you see some of the parts here, we have the electron source. We have the electron source here. The electron source. That way we have cathode and anode, and we have the electromagnetic specimen. Electron beam is specially focused using electromagnetic lens and metal apertures, and we have the sample holder. So a platform equipped with mechanical aim or aim for a mechanical arm for holding the specimen and controlling the position. And we have the imaging system, right? So imaging system, we have the imaging system with electromagnetic imaging, right? So this electromagnetic imaging is further divided into two lenses. One is the objective lens, and another is the projector lens. So and we have the fluorescent screen, phosphorescent screen, that is what incorporated into that particular device. So this is what some of the parts of the SEM. So the basic parts of SEM consists of electron source, electromagnetic lens system, sample holder, and image system. So these are the main parts of the transmission electron microscopy. So transmission electron microscopy is an instrumental technique. So if you come to the instrumentation, so it is an instrumental technique that uses a tiny focused beam of electrons. Transmission electron microscopy is an instrumental technique that uses a tiny focused beam of electrons. These electrons interact with a very thin and tiny sample. These electrons interact with a very thin and tiny sample. Usually only a couple atoms thick. Usually only a couple atoms thick. After passing through the sample, the electrons have changed course slightly and are detected by a photographic film or CCD camera. So after passing through the film, the electrons have changed course slightly and are detected by a photographic film or CCD camera. These electrons interact with a very thin and tiny sample, usually only a couple atoms thick. So the reason a temp can have such a large resolution factor at such a small size is due to the de Broglie wavelength of electrons. So this is just due to the de Broglie wavelength of electron. That is what we told when we study about the dual matter of radiation. So the reason of 10 having such a large resolution factor at small size is due to the de Broglie wavelength of electrons. The wavelength of electron lambda e is given by h by under root of 2m e naught into 1 plus e by lambda equals to h by under root of 2m e naught 2m naught e into 1 plus e by 2m naught c squared, right? So this is what the wavelength associated. This is what the wavelength which is being associated with de Broglie wave, and E is the energy of the accelerated particle. So the same when we consider for the Davis and Germer experiment, we have lambda equals to h by under root of 2me. So this lambda equals to h by under root of 2me can be written as 2m small e into E, where E is the accelerating electron which has the energy of 1.6 into 10 power minus 31 kg. 10 power minus 30 electron charge of the electron 1.6 into 10 power minus 19 coulombs, and we have the potential, the accelerating potential for a Davis and Germer experiment. In case of Davis and Germer experiment, the accelerating potential was supposed to be under root 54 volts, right? So where we observe some kin, in the angle, right? So this is what phi and lambda in the C. So this is what we observe, right? So this is the case where H is a Planck's constant, m naught equals 9.1 to 10 power minus 13 kg, and E is the energy of the accelerated electron, and C is the speed of light. So because electrons have wave particle duality properties, they can be produced at different, because the electrons have wave particle duality properties, they can be produced at specific energy and wavelength, and then be analyzed after being affected by sample. The maximum resolution angle which we obtain using Bragg's law, that is 2d sin theta equals 10 lambda, where we can find the interplanar spacing, or maximum resolution can be obtained as d equals to lambda by 2n sin alpha. This is what we obtain from X-ray diffractometer. 2d sin theta equals to n lambda, where d equals to n, for the first order, we write d equals to lambda by 2 sin theta. Right? If you take the rest mass, we have the mass. Right? So that is what maximum resolution is D equals to lambda by 2 n sin alpha and wavelength lambda and numerical aperture. Right. So the TEM consists of an electron gun made from a tungsten filament or lanthanum hexaboroid crystal. The electron gun is charged with about 100 to 300 kilovolts before any electrons of reasonable energy will be released from the source. Then a series of electromagnetic and electrostatic lenses direct the electrons into a beam. So this is what the series of electromagnetic and electrostatic lenses direct the electrons into a beam, right? So this is what we observe from this, right? So this is what the instrumentation. Right? So there are three set of lens. There are three set of lens of a typical transmission electron microscopy. One is, so that is a condenser lens which has electron beam, which is electron beam formation, and we have objector lens focus on beam onto a sample, and we have projector lens. Projector lens expands electron beam into analytical forms onto analysis screen or CCD. Magnification adjustments are made by varying the current through the quadrupole or hexapole lens. So this is what the electromagnetic optics that is to be introduced that were introduced. So that's why there are three set of lenses on a typical transmission electron microscope. So where we have the one is a condenser lens, projector lens, and objector lens. So condenser lens is nothing but electron beam formation. Objector lens is focus of beam onto a sample, and projector lens expands electron beam into analytical form onto analysis screen or CCD. Magnification adjustments are made. Magnification adjustments are made by varying the current through the quadrupole or hexapole lenses. So this is what the optics that was introduced. So if we come to the various components of transmission electron microscopy, we have the vacuum components, sample components, we have the electron lens components, aperture components. So if you see the vacuum components, the vacuum component or the vacuum system is approximated to 10 to 4 or 10 to 9 pascals. The pressure that is to be maintained inside the vacuum chamber is around 10 to 4 pascals or 10 to 9 pascals. Very important to prevent arc between cathode and ground. So very important to prevent arc between cathode and the ground. And the mean free path of electrons are to be calculated, right? So mean free path of electrons are to be calculated by taking the wavelength under consideration. The wavelength is what we obtain lambda equals to d by under root of 2m sin alpha, where we have used the previously expression when we see the theory component of, when we see the theory part of it, right? So next is a better beam focusing. So here we have less interaction with gas molecules. Here we have less interaction with the gas molecules. And if you see the sample components, generally the samples are deposited on different substrates. You have sample grids, usually 3 mm diameter mesh ring with 1 to 100 micrometer size squares made of copper, molybdenum, gold or platinum. Samples inserted into section with airlocks to prevent large decrease in vacuum pressure. Stages are designed to adjust the sample orientation when inside the TEM of more accurate readings. If you see the electron lens component, in case of electron lens component, focus parallel rays at a constant length. TEM lenses are usually the electromagnetic lens. That's why the optics are electromagnetic optics. So these electron lens components are made of generally the iron and alloys like iron cobalt and nickel cobalt because of their magnetic properties like magnetic saturation, hysteresis, and permeability. So if you come to the magnetic saturation and hysteresis, so for a ferromagnetic material, we have the hysteresis curves like this, right? We have for a ferromagnetic material, we have the hysteresis curve like this, right? So these hysteresis curves are taken between the magnetization and intensity of the magnetic field. So as we increase the field, so we obtain a saturation at point P. So if you further increase the field beyond this particular point, so it takes the reverse path. Right? And finally saturates at the initial part. So this is what we call it as the hysteresis loop. So this is what we call the hysteresis loop. The reason behind taking the reverse path is due to the important parameters like retentivity, due to the parameters like retentivity, and other is the coercive field. So due to this, it follows the reversible path, right? So and we have the permeability, and we have the one more parameter is permeability. Permeability is nothing but the lines of force what we see on the sample. So the aperture components are filter components that can stray from the beam path and affect image quality. Right, a decreasing in the beam intensity helpful with beam sensitive samples and can be fixed or movable depending on the quality of the instrument or manufacturer. And made of metallic substances thick enough to stop stray electrons but allow actual electrons through. So if you come to the electrons, if you come to some of the components like electron gun, So we have some electron gun. A high energy electron beam is produced by thermionic emission from directly heated tungsten filament. This electron beam is accelerated by the anodes towards the specimen. Magnetic condensing lenses, and the electron beam can be converged or diverged by the lenses. These lenses are usually of magnetic type, that is current carrying coils. The focal length can be controlled by the current through the coil of the magnetic lens. Right. So electron guns, we have different components as we told you. We have different components like electron lens component, aperture components, vacuum component, sample components, and then we have the electron gun, which is a beam of generating the electrons, which are produced by thermionic emission, right, from directly heating tungsten filament. So this electron beam is accelerated by the anode towards the specimen. So magnetic, we have some magnetic condensing lens. The electron beam can be converged or diverged by these lenses. These lenses are usually of magnetic type, that is current carrying coils. The focal length can be controlled by the current through the coil of the magnetic lens. So if you come to the construction of transmission electron, the magnetic condensing lens is used to condense the electron and is also used to adjust the size of the electron that falls onto the specimen. The specimen is placed in between the condensing lens and the objective lens. The main objective lens is used to block the high angle diffracted beams, and the aperture is used to eliminate the diffracted beam, and in turn it increases the contrast of the image. The magnetic projector lens is placed above the fluorescent screen in order to achieve higher magnification. The image can be recorded by using fluorescent screen or compact or closed circuit camera, CCD camera. So these are the internal component, and we have the working of the transmission electron microscope. So we have the electron bomb where the beam of electrons are generated. This electron gun is being collimated by using some magnetic condensing lens. So this magnetic condensing lens, the rays that are emitted from the electron gun are allowed to fall on a specimen. So where after falling on the specimen, they get diffracted and observe through some magnetic objective lens, and these not to get the fine beam, they are kept between the aperture and the projector lens are used to get the projected, and the projected image is obtained on the fluorescent screen. So this is what the internal structure, how the mechanism takes place, right? And here, if you see this figure, we have some electron gun here. So we have sample, so that we get the diffracted angle. So this is what the diffracted angle we see here. This is what the diffracted angle here. This is what the diffracted angle, which is an angle of 2 theta, where we can measure the intensity. We can measure the intensity and the diffracted beam. And this is what the transmitted beam, and we have certain oval sphere, which is a generation, right? A generation of oval sphere, right? So this is what the dark image field, and when we can see the difference between here, bright field image and dark field image, right? So in both we have the transmitted beam. One case we have this transmitted beam, and we get the diffracted beam. So all the other sides, so they are purely opposite. Here it is transmitted beam, here it is transmitted beam, here it is diffracted beam. Here it is transmitted beam, it is diffracted beam. These are some of the working of transmission electron microscopy. The stream of electrons are produced by the electron gun and is made to fall over the specimen using the magnetic condensing lens. Based on the angle of incidence, the beam is partly transmitted and partly diffracted. So both the transmitted beam and the diffracted beam are recombined at the evolved sphere, that is sphere of reflection, which encloses all possible reflections from the crystal satisfying Bragg's law to form the image. The combined image is called the phase contrast image. In order to increase the intensity and the contrast of the image, an amplitude contrast image has been obtained. So this can be achieved only by using the transmitted beam, and the diffracted beam has to be eliminated. So in order to eliminate the diffracted beam, the resultant beam is passed to the magnetic objective lens and the aperture. The aperture is adjusted in such a way that the diffracted beam is eliminated. Final image obtained due to the transmitted beam alone is passed to the projector lens for further magnification. The bright field image obtained is purely due to the transmitted beam alone. So the dark field image obtained due to the diffracted image. So here we can see the differences between the diffracted image and the transmitted image. Diffracted beam and the transmitted image here, right? The diffracted beam and the transmitted beam. So the bright field image obtained is purely due to transmitted beam alone, whereas in case of dark one, we obtain due to the diffracted image. So this is how we can find that we can find the bright field and diffracted, where we can find the bright field and the dark field, which is due to the transmission and the other is due to diffraction. Right. So what is the purpose of using transmission electron microscope? A transmission electron microscope is able to form image of sample molecules and and atoms tens of thousand times smaller than any visible light microscope. Using the stage running, a tilt series can be developed to resolve 3D images of samples. So what we can do with this transmission electron microscopy is that we can see the scan types and uses. Right. So you have the bright field, diffraction contrast, dark field images, crystallographic lattice defects, biological specimen many, subatomic ratios. So what are the advantages and disadvantages of using this transmission micro? So if you see some of the advantages, we can see some of the pros. So the advantage is we can find the sample at we can find the specimen of the sample, the atomic structure of the sample can be seen at very high resolution and requires very little sample to test. We don't require a bulk sample. A small sample is required to get the resolution form. That's why very high resolution requires very little sample to test. It is a quantitative and qualitative form and can be modified in many ways to account for different substances and requirements. What are the cons? So tough sample preparation or consuming runs to get a few images. Small field of view may take several runs to find what is being studied. And we have the sample destruction, especially biological samples. So this is what the disadvantage. We have the tough sample preparation, our consuming runs to get a few images. Small field of view may take several runs to find what is being studied. Sample dissection, especially biological sample. Right. What are the advantages and disadvantages? Advantage, it can be used to examine a specimen of size of 0.2 nanometers as we told. And the magnification is 1 lakh times greater than the size of the object. It has high resolution. And the resolving power is 1 to 2. And the disadvantages is the specimen should be very thin. It is not useful for thick samples. Only thin samples can be fabricated. And 3D image cannot be obtained. We obtain only the 2D image. There are three images. There are certain changes for the structural change due to the sample preparation. Right. So in case of biological samples, the electrons may interact with the samples, which may even damage the samples. So these are some of the disadvantages. And if you come to the applications of transmission electron microscopy, the main application of transmission electron microscopy is in nanoscience and technology to find the internal structure of nanomaterials, in the nanoparticle. It is used to find the two-dimensional image of very small biological cells like cells, virus, bacteria. It is used to find the 2D image of very small biological cells, virus, and bacteria. The main application of TEM is in nanoscience, used to find the internal structure of nanomaterial. Right. So these are some of the applications. If we come to the summary, the overall TEM is useful for small nanoscale systems. TEM can create 3D images of samples. TEM can be modified. TEM can be modified for different types of molecules and atoms. It is not a cheap equipment. It's a very costly equipment. The transmission electron microscopy is good, and that's the way the cookie crumbles. So these are the references what we used to define to study to collect some slide information and all. So these are the informations what the references. Kirkland E19 Advanced Computing Electron Microscope, the Springer publication, Hubbard, the Handbook of Surface Imaging and Visualization, CRC Press, and we have all the books related to Springer publication. So these are some of the references, right? So these are what explained.
Like, share and subscribe. Hit the bell icon for more updates.